Hello friends, in the preceding lecture we learned that an electrostatic force acts on particle 1 due to the presence of particle 2. We also found the force direction, and given some data we can calculate the force magnitude also. However, here is a leftover nagging question: how does particle 1 know of the presence of particle 2? That is, since the particles do not touch, how can particle 2 push on particle 1? How can there be such an action at a distance? One purpose of physics is to record observations about our world, such as the magnitude and direction of the push on particle 1. Another purpose is to provide an explanation of what is recorded. Our purpose in this lecture is to provide such an explanation to this nagging question about electric force at a distance. The explanation that we shall examine here is that particle 2 sets up an electric field at all points in the surrounding space, even if the space is a vacuum. If we place particle 1 at any point in that space, particle 1 knows of the presence of particle 2 because it is affected by the electric field particle 2 has already set up at that point. Thus, particle 2 pushes on particle 1 not by touching it as you would push on a glass of water by making contact. Instead, particle 2 pushes by means of the electric field it has set up. Our goals in this lecture are to define electric field, discuss how to calculate it from various arrangements of charged particles and objects, and discuss how an electric field can affect a charged particle. The electric field. A lot of different fields are used in science and engineering. For example, a temperature field for an auditorium is the distribution of temperatures we would find by measuring the temperature at many points within the auditorium. Similarly, we could define a pressure field in a swimming pool. Such fields are examples of scalar fields because temperature and pressure are scalar quantities having only magnitudes and not directions. In contrast, an electric field is a vector field because it is responsible for conveying the information for a force which involves both magnitude and direction. This field consists of a distribution of electric field vectors, one for each point in the space around a charged particle. In principle, we can define electric field vector at some point near the charged object, such as point P, with the following procedure. At point P, we place a particle with a small positive charge Q0 called a test charge because we use it to test the field. We want the charge to be small so that it does not disturb the object's charge distribution. We then measure the electrostatic force that acts on the test charge. The electric field at that point is then E is equal to F upon Q0. Because the test charge is positive, the two vectors in equation A are in the same direction. So, the direction of electric field is the direction we measure for electrostatic force. As shown, we always represent an electric field with an arrow with its tail anchored on the point where the measurement is made. This may sound trivial, but drawing the vectors any other way usually results in errors. Also, another common error is to mix up the terms force and field because they both start with the letter F. Electric force is a push or pull. Electric field is an abstract property set up by a charged object. From equation A, we see that the SI unit for the electric field is the Newton per coulomb. We can shift the test charge around to various other points to measure the electric fields there, so that we can figure out the distribution of the electric field set up by the charged object. That field exists independent of the test charge. It is something that a charged object sets up in the surrounding space, even vacuum, independent of whether we happen to come along to measure it. For the next several discussions, we determine the field around the charged particle and various charged objects. But first, however, let's examine a way of visualizing electric fields. Electric field lines. Look at the space in the room around you. Can you visualize a field of vectors throughout that space? Vectors with different magnitudes and directions. As impossible as that seems, Michael Faraday, who introduced the idea of electric fields in the 19th century, found a way. He envisioned lines, now called electric field lines, in the space around any given charged particle or object. This is an example in which a sphere is uniformly covered with negative charge. If we place a positive test charge at any point near the sphere, we find that an electrostatic force pulls on it towards the center of the sphere. Thus, at every point around the sphere, an electric field vector points radially inward towards the sphere. We can represent this electric field with electric field lines as shown in this figure. At any point, such as the one shown, the direction of the electric vector at that point. The rules for drawing electric field lines are: at any point, the electric field vector must be tangent to the electric field line through that point and in the same direction. In a plane perpendicular to the field lines, the relative density of the lines represents the relative magnitude of the field there, with greater density for greater magnitude. If the sphere, as shown in figure, were uniformly covered with positive charge, the electric field vectors at all points around it would be radially outward, and thus so would the electric field lines. So we have the following rule. Electric field lines extend away from positive charge where they originate and towards negative charge where they terminate. As in the case of sphere, they originate on a distant positive charge that are not shown and are moving towards the negative charge. For another example, figure shows part of an infinitely large non-conducting sheet or plane with a uniform distribution of positive charge on one side. If we place a positive test charge at any point near the sheet on either side, we find that the electrostatic force on the particle is outward and perpendicular to the sheet. The perpendicular orientation is reasonable because any force component, that is, say upward, is balanced out by an equal component, that is downward. That leaves only outward, and thus the electric field vectors and the electric field lines must also be outward and perpendicular to the sheet as shown in these two figures. Because the charge on the sheet is uniform, the field vectors and the field lines are also uniform. Such a field is a uniform electric field, meaning that the electric field has the same magnitude and direction at every point within the field. This is a lot easier to work with than a non-uniform field where there is a variation from point to point. Of course, there is no such thing as an infinitely large sheet. That is just a way of saying that we are measuring the fields at points close to the sheet relative to the size of the sheet, and that we are not near an edge. This figure here shows the field lines for two particles with equal positive charges. Now the field lines are curved, but the rule still holds. The electric field vector at any given point must be tangent to the field line at that point and in the same direction as shown for one vector, and a closer spacing means a larger field magnitude. To imagine the full three-dimensional pattern of field lines around the particles, mentally rotate the pattern and figure around the axis of symmetry, which is a vertical line through both the particles. Electric field due to a charged particle. After going through this section, you should be able to draw a charged particle, indicate its sign, pick a nearby point, and then draw the electric field vector at that point with its tail anchored on the point. For a given point in the electric field of a charged particle, identify the direction of the field vector when the particle is positively charged and when it is negatively charged. For a given point in the electric field of a charged particle, apply the relationship between the field magnitude, the charge magnitude, and the distance r between the point and the particle. If more than one electric field is set up at a point, draw each electric field vector and then find the net electric field by adding the individual electric fields as vectors, not as scalars. Electric field due to a point charge. To find the electric field due to a charged particle, often called a point charge, we place a positive test charge at any point near the particle at a distance r. From Coulomb's law, the force on the test charge due to the particle with charge q is equal to 1 upon 4 pi epsilon 0 into product of q and q0 divided by r square into unit vector r. As previously discussed, the direction of force is directly away from the particle if q is positive and directly towards it if q is negative. From equation A, we can now write the electric field set up by the particle at the location of the test charge as E is equal to F upon Q0, which is equal to 1 upon 4 pi epsilon 0 into Q upon R square into unit vector R. Let's think through the directions again. The direction of electric field matches that of the force on the positive test charge, that is directly away from the point charge if q is positive and directly towards it if q is negative. So, if given another charged particle, we can immediately determine the directions of the electric field vectors near it by just looking at the sign of the charge q. We can find the magnitude at any distance r by converting equation B to a magnitude form as E is equal to 1 upon 4 pi epsilon 0 into q upon r square. This equation gives magnitude E only. We must think about the directions separately. The figure here gives a number of electric field vectors at points around a positively charged particle, but be careful. Each vector represents the vector quantity at the point where the tail of the arrow is anchored. The vector is not something that stretches from a here to a there as with a displacement vector. In general, if several electric fields are set up at a given point by several charged particles, we can find the net field by placing a positive test particle at the point and then writing out the force acting on it due to each particle, such as F01 due to particle 1. Forces obey the principle of superposition. So we just add the forces as vectors as F0 is equal to F01 plus F02 and so on up to F0n. To change over to electric field, we repeatedly use equation A for each of the individual forces and get E is equal to F0 upon Q0 and is equal to F01 upon Q0 plus F02 upon Q0 and so on up to F0n upon Q0, which is equal to E1 plus E2 and so on up to En. This tells us that the electric field also obeys the principle of superposition. If you want the net electric field at a given point due to several particles, find the electric field due to each particle, such as due to particle 1, and then sum the fields as vectors. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. A charged particle sets up an electric field in the surrounding space. If a second charged particle is located in that space, an electrostatic force acts on it due to the magnitude and direction of field at its location. Electric field lines help us visualize the direction and magnitude of electric fields. The electric field vector at any point is tangent to the field line through that point. The density of field lines in that region is proportional to the magnitude of the electric field there. Thus, closer field lines represent a stronger field. Electric field lines originate on positive charges and terminate on negative charges. The electric field vectors set up by a positively charged particle all point directly away from the particle. Those set up by negatively charged particles all point directly towards the particle. If more than one charged particle sets up an electric field at a point, the net electric field is the vector sum of the individual electric fields. Electric fields obey the superposition principle. So friends, that is it for today. See you in the next lecture where we shall be talking about electric field due to various objects such as a dipole or a charged disk. Thank you very much.